this example, the region R bounded by the following curves. The curves we are given is y equals x minus x squared and the line y equals 0. The problem asks you to use the shell method. When you use the shell method, that means the shell or the slice or the partition is parallel to the axis of revolution. Okay, the graph y equals x minus x squared is the parabola graph, opens down because the highest power 2 has a coefficient as the negative side. If you want to do by hand or do it a quick graph, you can look at the intersection or the y in the x-intercept, sorry. So factor the x out, you get x times 1 minus x. So you can see that when x equals 0, y 0, when x equals 1, y 0. And then since the negative side tell you the graph, the parabola opens down. So you can do the quick sketch, like the graph as the opens down parabola passing the point 0 and the point 1. And also given like y equals 0. So y equals 0 is the x-axis. That's why the region bounded by this graph, by these two graphs, is in the green area here. The axis of revolution is the y-axis. So this is the axis for this problem. Now, when you perform the shell, we call the partition gonna be parallel to the axis of revolution. Once you see the bar on the region, this bar is on the x-axis, so this is the x position. X position, the following part, x is bounded by 0 and 1 because the bar moves to the left and to the right within the region. It will not go lower than 0, it will not go beyond 1. And this is our interval of integration. Okay, and the next part, since we see the bar landing here, we can tell that the thickness here, that is the delta x. Okay, delta x. Okay, so delta x is the same as dx. So we put here dx, or delta x is the thickness of this problem. Then if you rotate the bar here about the x-axis, the y-axis, it's from the shell or the cylindrical shell here. Okay, we take one piece out, and then to find out the rest of the problem, which is the radius and the height of the bar. For the radius, you measure from the axis of revolution to the bar. So that's the radius. Okay, let me make the bigger one. When I write down here, so radius. The measurement from the left to the right. The right is the bar position, which is the x, and the left is the 0. So then the radius is x. Okay, and next the height of the shell. The height of the shell is gonna be the height from the top of the graph to the base of the graph, which is from the function value or the function x minus x squared. Put the over here, so the height or the h equals x minus x squared. Okay, now we got everything. We're gonna set up the integration to find the volume. Volume by shell equals 2 times pi times r. R as the radius is the x. do the antiderivative, right? This is a 2 pi r times the height. The height is x minus x squared multiplied by the thickness, which is dx. So this one is the circumference, and this one is the radius, and this one is the height, and this one is the thickness. Integration from 0 to 1. And in the cleaner up portion, the 2 pi is the coefficient. Get out of the way. Integral from 0 to 1. And the piece here, the integrand, simplify as much as you can before you do the antiderivative. Right? So it's going to be like x times x and x times x squared to become x squared minus x to the third with respect to x. The rest of the process, just go back to the skill problem as you find the antiderivative term by term. So this can be 2 pi x to the third over 3 minus x to the fourth over 4. Evaluate from x equals 0 to x equals 1 equals 2 pi 1 over 3 minus 1 over 4 minus 0 minus 0. And the number comes out to be pi over 6 as the volume of this solid of revolution.